This week we're moving on to our first inferential statistic. Everything pretty much that we've done up to this point has been descriptive statistics until we learned about hypothesis testing. And hypothesis testing is what's prepared us for inferential statistics. Remember that inferential statistics are meant to try and draw conclusions about a population from a sample. So let's do a little review of hypothesis testing because we're going to be using this in every single statistic that we learn from here on out. First, remember that what we're really looking for is to see whether a statistical score jumps the quote-unquote hurdle or not. And here what we mean by hurdle is the critical region, those areas on the end of the distribution, on the one end if you're doing a one-tailed test, or a split between the two tails if you're doing a two-tailed test. And remember that what we count as our critical region in social sciences is cut off by the alpha of 0.05. So if you're running a one-tailed test, all of that 5% is in one tail or the other. If you're running a two-tailed test, that 5% is going to be split up to 2.5% in each. But what we're really looking to see is, does our statistical test jump into those critical areas? In the outputs that we'll be looking at in PSPP, what this is going to be translated to is looking for a p less than 0.05. If your statistical value is not p less than 0.05, that means that it didn't jump into the critical region. So what you'll conclude is that you'll retain the null hypothesis. And remember that we only test the null hypothesis, not the alternative hypothesis. If your value does jump into the critical region, then you reject the null hypothesis. So that's the conclusion that we're going for. Either we're rejecting or retaining the null hypothesis. So back to the t-tests. The one that we're learning about this week is only the first of many t-tests. These are the 3 different kinds that we will eventually learn about, each in the next 3 weeks. And this is just to give you a heads up. I want to talk a little bit about the t-test generally. So we'll start by looking at the t-distribution. Remember that the z-scores that we looked at had their own distribution. It's the case that pretty much every statistic has its own distribution, and they all look slightly different. So here we have the t-distribution. The t-distribution is a lot like a normal distribution, but it actually changes a little bit based on the sample size, on the n. And here you can see a couple of variants of different n sizes that cause the curve to shift a little bit. What this means is that the value that cuts off the critical regions or critical region is going to vary based on the sample size. Now, if you were going to be doing this by hand, you'd actually need to look up the critical regions in the t-table, and you can find the t-table in Appendix C. So when they're talking about that in the book, and if they ask you to ever find any critical values by hand in the homeworks, that's the table that you're going to want to use. Really, though, we're going to be focusing mostly on using the p less than 0.05 value in PSPP. So let's talk specifically about the one-sample t-test now. The purpose of the one-sample t-test is to compare a sample to a population. So what you're taking is, if you have a sample and you want to know, is this different than the population, you would run a one-sample t-test. So as an example, let's say that the average grade across all of my CWI classes is a 75.23. Now there are 25 of you in my PSYC217 online class, and let's pretend that your average score right now is a 78.11 with a standard deviation of 10.03. What we could ask using the one sample t-test, is the PSYC217 class, the sample, different than all of my classes, the population? Just to clarify the difference between the one sample t-test and the z-score that we looked at before, because the formula is going to look quite similar, is a z-score can only be used when you know the population variance. And the reality is that we very rarely know anything about the actual population. The reality is that mostly we're going to be using samples to try to make some generalization about the population in inferential statistics. So you use the one sample t-test when you only know the sample variance as opposed to the population variance. Okay, so let's go ahead now and apply hypothesis testing to the one sample t-test. So remember, the first thing that we'll always do is start with our null and alternative hypothesis, and this will be true regardless of the test that we're looking at. A null hypothesis might be that the PSYC217 class scores are not different than the population scores of all of my classes, whereas an alternative hypothesis would be that the PSYC217 scores are different from all of my classes. Now the book gives you the formula, and here we have it here. You take the mean and subtract the mu and divide by the variance, and this will give you a t-value. And then what you would do is you would take that t-value and compare it to the critical value, and we'll talk about that in the next step. Or you can get the t-value in the PSPP output, which in the homework is what I'm going to be asking you to do, entering the data into the PSPP program, running the statistic, and then looking for the output from that data analysis. Regardless of how you get it, that's the point of this step, is to find the actual t-value. And then we have to make a decision about that t-value. So remember, what we're looking to see is, does our t-value jump into the critical region or not? So if you had done it by hand, you would need to use the degrees of freedom value and the alpha of 0.05 to get the critical value in the t-table, which is in the appendix. Or in the homework, you're going to be asked to look at the p-value in the PSPP output. So remember, p less than 0.05 means that you reject the null hypothesis. A p greater than 0.05 means that you retain the null hypothesis. When you've rejected the null hypothesis, your value has jumped into the critical region. When you retain the null hypothesis, your value has not jumped into the critical region. And finally, you're going to start writing your results up as an official APA document. So there's an additional explanation about how that should look. So make sure to follow that carefully. In APA, formatting is important. I will be grading just as much on formatting as I will be on the actual results. One last thing to say is I briefly had mentioned the term degrees of freedom a couple slides back, and I wanted to say something specific about that because it can be a little bit hard to understand. Degrees of freedom was something that I probably really didn't understand until I had taken maybe my 4th statistics class, but I do want to throw it out there in case some of you are wondering what the heck is this DF value. So DF stands for degrees of freedom, and we're going to see a DF in every single statistical test we run from here on out. It's going to be a value that is oftentimes a reflection to some extent of the sample size. So the degrees of freedom essentially is a number that tells us the number of the scores in the sample that are free to vary. And the book explains this a little bit by giving a hands-on example. There's also an explanation at Wikipedia that says that it seems to be an abstract, mythical idea to many stats students, and I think that that's very true. So the point here is that if you don't understand what a degrees of freedom is or how it came to be, don't worry. Mostly I just want you to know that when it says DF, you're being asked for the degrees of freedom, and that for every statistical test there are a different way of getting the degrees of freedom, and it represents some very abstract idea. So if you want to know about that, you want to look into it a little bit on your own, but again, if you don't and it confuses you, don't worry too much about it.